So thank you everybody to be here again. So this is the third lecture of our joint mini course with Jerome BUZZI. So yesterday I finished the talk talking about Margulis measures or phi Margulis measures. I briefly just remind you, we typically have a foliation. So again, suppose here we have an expanding foliation. You can, as I said, for my purposes, you can consider always a partial hyperbolic diffeomorphism, and Fu will be the expanding foliation or unstable foliation. Then a Margulis family, phi Margulis family of measures are measures which are supported on leaves, Fu leaves. They are Radon measures. So they charge finitely the compact subsets of the leaf. And the most important property is this phi conformal property, So they have the right Jacobian, F star of mu x is equal to exponential of phi minus the potential mu of fx. Okay? So for the purposes of today, let me just consider the case of maximal entropy. So the phi will be 0. So today, phi will be constant. And when we talk about Margulis family, we are just talking U Margulis family. We are just talking measures which are conformal in the unstable direction. So you are kind of linearizing mu of x, f of x. Okay, so you are putting some coordinates or some. Yeah, this is the definition. Yes, it will be entropy in some cases. So as I told you, by Le-Drapier arguments, etc., you can conjecture what is P. The construction of these measures are very important, and maybe historically Sinai constructed these kind of measures, and then Margulis used these constructed such measures to study anosov flows. And these measures, as Paolo was commenting, are very important to understand the conditional measures of maximal entropy. So in fact, MUs are the right candidates for the conditional measures of UMMEs. Okay? So of course, you are considering just unstable foliation. So you will have conditional measure of unstable, conditional measure of UMMEs. Then the result, this is in fact a result, but I'm not writing this result today. These measures are the candidates, in fact the conditional measures of UMMEs, and for partial hyperbolic diffeomorphisms. But the problem is that construction, one important task is how to construct such measures. So as I told yesterday, there are few technologies. Typically, you use a functional analysis approach, a fixed point theorem, or you have some Cartier-Dori construction. In some cases, it works. So let me just put one of the last results that I know. This is a result joint with Jerome BUZZI, Sylvain Corbusier, and Maurizio Poletti. Well, this is just for the Margulis families. So consider F, M to M, C1 plus alpha. I need always some Holder regularity. And T of M is decomposed into two bundles, ES plus EC. So here ES is uniformly contracting. ES is uniformly contracting. Suppose that you have FCX, foliation tangent to EC, then there exists a family, at least a family of measures defined on the whole manifold, which are Margulis family, a zero Margulis family, or constant Margulis family. Well, okay, this may be useful in some setting. It is not still the most generic thing that you can imagine, of course, for Margulis families, but at least in partially hyperbolic setting, it is going to be useful to obtain some results. Well, again, here I just said constant Margulis family, but there is also result by Pablo. Well, it is in the same realm, in fact, these results are in the same realm. Pablo, Carrasco, and Federico, where you can also do it for phi Margulis family. Well, sorry? What is positive?
No, P.
P, okay, P is positive, yes.
So that means that the central
No, it is not necessarily, it is not saying you that it is expanding. You have some measure. But you don't know what is the nature of the measure. The measure can be something which is very meager. Okay? So, yes. You have just, in the transverse bundle, you have uniform contraction. You need something transversal such that you have uniform contraction. In fact, you don't need even this kind of structure, differential structures for these things. You need just some contraction topological. But okay, but in fact, something is important here is that, you need really C1 plus alpha because you know that the stable foliation is absolutely continuous. So maybe one important comment is that you have Fs, which is absolutely continuous. So this is important. So as you can see, these measures, MC measures, are going to be transverse measures for the foliation Fs. So what are you looking for in this case? So if you remember your topology course, if you have a foliation, you can define the notion of transverse invariant measures. It is defined on the transverse subset of transversals. And as soon as you have a measure like this, MC, such that you have this conformal property, this means that you have a measure on the transverse such that has some conformal property. Okay, so this story goes further. I do not plan to talk about exactly the Margulis measures, but what is important for me is that these measures satisfies this good property, and furthermore, what you know is that these measures are invariant by Fs holonomy. So the constant Margulis measures, Margulis MC, are invariant by Fs holonomy. Okay? So if you have some potential, then it is a bit subtle to have these measures to be, well, in fact, the idea is similar to the Margulis construction, but you can prove that this measure always exists, okay? So why they are interesting? Because, okay, so let me just finish this introduction about Margulis measures. I have a partially hyperbolic diffeomorphism. So I would like to understand the MMEs. So a roadmap to construct MME, okay? So to construct UMME, you can just take U Margulis measures if you can construct. But the problem is that, as you see here, the way that I can prove the existence of Margulis measures is technically, I need some transverse foliation direction which is uniformly hyperbolic. So what we can do here is to construct ECU or either MCU measures, and similarly you can construct MCS measures, okay, measures. So the problem is that you need a measure on EU, exactly. I didn't construct any MU measure. So you see everything was on unstable foliation. But constructing a measure on the strong unstable leaves is not addressed here. So these things are really pushing forward, further the Margulis ideas. Of course, let me just remind you here something is hidden, and something is new here with respect to the previous work that we had with Jerome, Todd Fisher, and myself. We had this thing, but assuming that this foliation is minimal. So FS was minimal. Okay, so, well, you do not need assume minimality, and in general you can construct the similar ideas. So, but anyway, you do not have measure up to now. So far, I have not a measure on unstable foliation, which is the important thing for us. Okay, so this is the difficulty, and the difficulty is solved in some cases. For instance, in Pablo and Federico's paper, they assume that, suppose that F is center isometry. So if you have center foliation, any dimension, and the action of F is isometry there, you can induce a measure from MCU to MU. Okay, we have F, more general situation that we have, a discretized annus of flow, that I can define a bit later. Then you can construct, there exists MUX, X belonging to M. So you construct the measure CU using this abstract functional analysis technology, fixed point theory, and then from MCU you will get your measure. This is center unstable leaves, and here are unstable leaves. Here is center. Okay, so you want to induce a measure on FU, and then you use some properties of the dynamics to construct this measure. Okay. As soon as you construct these measures in this way, using this induction process, so you essentially, well, very caricature, is that you just define the measure in some fundamental domain, the measure of some subset in the unstable foliation as the CU measure, MCU measure of a fundamental domain. As soon as you define in this way, you can prove that MU also is conformal. Well, it will be phi conformal. Okay, I said you phi is 0 today, so let me maintain 0, because as soon if it is not 0, then you need to work. And I don't know to do it yet. So if it is constant on the center leaves, yes. Okay, so if phi is essentially nothing on the center, you can repeat the things. But for general potential, not yet. But for today, for the sake of the lecture today, you have it. And so this is really the candidate for the disintegration of the measure on the unstable foliation. And then one of the most important things, so most important property of these measures is that, which enable us to use Hopf-type arguments, is that MUX is absolutely continuous. Absolutely continuous, I mean by absolute continuity with respect to FCS holonomy. So this means that if you consider unstable foliation, unstable was horizontal, unstable foliation, so you have measures on leaves. If you travel from one measure to another measure using CS direction, you have absolute continuity. In fact, you have 0 measures goes to 0 measure with respect to this measure. Okay, so this is essentially what you use to prove ergodicity of measures in using Hopf-type argument. So these things enable you to prove uniqueness or finiteness of measures of maximal entropy. So these are encapsulated in some results that I try to talk with you. Okay, so let me now go to another part of the talk, which is the invariance principle. Invariance principle. Okay, I have 15 minutes to talk about the invariance principle, but fortunately last year, Yuri Lima and Mauricio Poletti gave 4 lectures, I suppose, just about invariance principle. So just push the button and look and watch the mini course of Poletti and Mauricio Poletti and Lima Poletti mini course in ICTP mini course 2024. Well, but I should say something here for you in 15 minutes. So what is invariance principle? Invariance principle is very related to the talk of Aaron in the first talk, and maybe it will appear. It is kind of getting, the philosophy is getting invariance of these integrations along center leaves by unstable or stable holonomy, or any other in the abstract setting. If you remember the skew product case, you want to say that the disintegration along the fibers of the skew product are constant on the future or in the past, as it was announced by Aaron, the abstract model. And it is, I think, well, the history is long. Maybe I should say Furstenberg. Well, then again, Francois did the first breakthrough when you go to the co-cycle setting. Well, there are people like in other setting, Crowell, Baxendale, in one-dimensional setting or differential equation setting. We cannot forget the result by Christian, Bonatti, Gomez-Mont, and Marcello, when this invariance principle and co-cycled and Lyapunov exponents are appearing in more understandable vein for the young people who are working on co-cycles. Then we have Avila, Viana, when they generalized these results to the diffeomorphism case. Okay, and today I will not talk about these results, of course. I will talk about an entropic version, hidden in these results of invariance principle. And this is a result that we did now, it is a long time ago, with Jiagang. So myself and Jiagang. For some other reasons that it appear today. And it is as follows. So the invariance principle says that. So the setting is as follows. Consider f from m to n, m times n. This is a measurable fiber bundle. Okay, so you have a measurable fiber bundle. Okay, you have a measure. Of course, here you have a measure, mu. Okay, my invariant measure is always mu for the top. And suppose that, so let me just do the pictures. M times n and mu, I have a map, a fiber bundle map, such that it covers some, in the base, it covers here, a dynamics, m. So m here is pi, m is pi star of mu. Okay? So in principle, fibers can be any manifolds, compact or non-compact space, but here you need some fiber bundle structure. Okay? Now suppose that you have a partition here on M. So I will make the pictures again. You have a partition here in M. The partition is sigma, okay? And you have a partition which is preimage of this partition on M times N, which I call psi Cu. So you can imagine this is the center unstable. And this partition is refined by another partition which is psi U, which is the unstable partition, in fact. So you can imagine everything here. You consider your favorite partial hyperbolic skew product. And what we prove, the result, is that the entropy, unstable entropy, so the entropy along this psi U, so everything is here is a measurable partition or countably generated, as Jerome called them. So sigma is countably generated partition, and so it will happen for psi U also. So what we have is that HU of F and sigma, this is always less than or equal than the entropy of sorry, F. F is the fiber bundle, okay, and mu is less than H of F or M and sigma. Yes. So here, if you want to write it better, this is H of F. The measure mu with respect to the partition psi U is always less than the entropy of M with respect to F and sigma. Okay, so if you want to remember this, this is saying that the conditional entropy along the foliation upside is always less than the entropy downward. So just to remember this, just consider this fake intuition that the entropy up is less than the entropy down, okay? Which is typically is not intuitive, but okay, this I'm just cheating in this intuition. So, and the equality occurs, equality, if and only if your measure is really kind of product measure here. So if and only if the pi star of so if and only if psi u, mu psi u, okay, here, psi u of x, almost everywhere is equal to m sigma of pi of x for mu almost every x. So what I'm saying is that the measure sitting here on any unstable plaque is exactly equal to the measures that you have here on the projection. Yes?
So sigma and taking m as the center.
I'm not assuming anything about these things.
So
Expansion.
sigma can be any partition on m, or
Sigma any good partition. I mean, what is good partition? Good partition is a countably generated partition. Okay? With respect to this measure. You will see in a second that what I'm saying when I say the model. Okay. Any other question? So, yes. Huh? Yes, I projected the measure mu. M is P star of mu. Oh, you cannot see it over there. M, yes? M is pi star of mu. So where? Here? Oh, well, okay. Okay, no, okay, you are right. So I'm saying that these measures, so you take any subset here, you can project. Yeah, you should project the measure. So pi star. Thank you very much. Yes. Okay, any other question? So I erase, you can see what is. So one model for application of this thing is invariance principle, is when you have dynamics, which is kind of a skew product, and you have some information about the unstable entropy of the dynamics, okay? And then you want to conclude some invariance principle. So let me just give an application. Well, before application, let me just say you something other. Measure theoretic comment. So I said that if you have the equality in the entropy formula there, over there, what happens is that the measures on the leaves, on the unstable plaques, are invariant by the holonomy of the center foliation here, okay? So every measure, if you take any point x and y, what I'm saying there, in particular, is telling that if you go by the, here is center, here is unstable. If you go by the center holonomy from x to y, okay, and you push forward the unstable measure on x, you get unstable measure on y. Okay, so this is that I am saying there. And a measure theoretic comment is that this is equivalent to say that the measure is product. This is equivalent to say that if you consider the unstable holonomy from now the unstable holonomy from one point x, for instance, is x to z. The unstable holonomy from x to z, and if you push forward the measure which is on the center plaque of x, then you get the measure on the center plaque of z. Okay, so this is a Fubini. This is essentially this is an exercise. No. This is a measure theoretical comment. You consider a space with two transverse. Consider a square with two transverse countably generated partitions. Okay, and you have a good notion of holonomies, and you have a measure mu in the square. Then you disintegrate your measure. What I'm saying is that if by chance the unstable disintegration is invariant by the C holonomy, then you can show that the center disintegration is also invariant by the U holonomy. So this is I'm putting as an exercise. This is really using the Fubini change of the integrations. So this is because if you go from one point by holonomy to some point here and go here, it is the same as going by the C holonomy and then by U holonomy and then by C holonomy you get to the same point. So I need this product structure for these two foliation, two plaques. Okay? So this is a product structure. This is a topologically product structure. Then you have this thing. So, okay. So this means that what I announced here, I'm saying that if you have the unstable entropy equal to the entropy downward, okay, here in the base, then we can prove in the invariance principle, entropy version of invariance principle, that the measures on the unstable leaves are invariant by the center holonomy. This is exactly saying that if you take any subset here, the measure of this subset is the same as the measure of this subset, which is coming by the holonomy, center holonomy. So this means that by that comment, this means that in particular, this integration on the center direction will be also invariant by the unstable holonomy. Okay? So the invariance principle there, the invariance principle is saying equivalently by the cost of measure theory course, LEM, that mu C is invariant by psi U holonomy, FU holonomy. So what is FU holonomy? In the abstract model, it is just define everything abstract that you have just this partition. In each plaque, I'm saying that if I disintegrate, then you have the invariance by the unstable holonomy. Holonomy defined by CU. Okay? So far, so good? Yes, not good? Yes. Pi, yes, pi is injective on any element of psi u. Yes, thank you. On any element of psi u, pi, maybe I write it here. Pi is injective on any psi u of x. I'm assuming that here I have in the model of product, that product. Yeah. So okay. Let me just make an application of this, is that if you consider f from m to m, so suppose that this is a partially hyperbolic diffeomorphism with circle center leaves or compact center leaves. And suppose that the quotient space, the quotient by the center leaves, you have a dynamics which is an Anosov homeomorphism. Okay? So you quotient down the dynamics by the center leaves, assume that it is Anosov. So suppose that the dynamic is C1 plus alpha, and you have a measure such that all the Lyapunov exponents along the center are 0, or in fact are non-positive. All the Lyapunov exponents are non-positive. Then the center disintegration of the measure is U invariant. Okay? So okay, so here this is just fitting in the hypothesis of the invariance principle, because the entropy, the unstable entropy, so here you have unstable foliation, you have good partitions subordinated to unstable foliation, as told before. You know that the entropy of unstable entropy of F with respect to measure mu is less than the entropy of the measure. Sorry. It is equal to the entropy of the measure. Okay? The unstable entropy is equal to the full entropy of the measure. This is because you have just 0 exponent or non-positive exponent on the center. And here you use Le Drapier-Young, okay? So you're using the fact that the full entropy of a measure is the sum of unstable entropy plus remaining entropy, okay, times the dimensions, but you don't, Lyapunov exponents times dimensions, but you do not do, okay, HF mu is equal to entropy plus sum of some lambda j plus dj, which are the dimensions, corresponding dimension, and the other Lyapunov exponents that you may have, you do not have, so you are in this case. You can apply the invariance principle, okay, and say that by invariance principle, mu Cx are U invariant. Okay. Let me announce also another invariance principle in the setting of partially hyperbolic diffeomorphisms that cannot be proved using this abstract invariance principle that I announced for you, which is another result given by Courvoisier and Poletti, which says that suppose that F from M to M is a C1 partially hyperbolic diffeomorphism, and suppose that it is quasi isometry along center foliation. So you assume that there exists a center foliation along center foliation. So suppose that you have a measure which is invariant by F, and mu some ergodic measure, such that the U entropy of the measure is equal to the full entropy of the measure, okay? So here is the unstable entropy equal to the full entropy. What they prove is that in this case, you can conclude again that mu Cx is U invariant. Okay, so you should be careful to define what is disintegration along center leaves when your leaves are not compact or you have not a measurable partition, but you always define these things projectively. And I should define for you what is quasi-isometric. A quasi-isometric property means that if you iterate, okay, there exists some okay, the size of if you take the image of the center ball around the point of size epsilon, this is inside the ball of X. So for large K, there exists some L such that for large K, BC of Fn of BC is inside BC of Fnx, and maybe a bit larger ball, and it contains also the BC center ball of maybe K divided by L. Okay? So the center balls do not grow too much, and they do not shrink too much also for all iterates, for every n, for every positive n. Here is C1. So everything when you don't have Lyapunov exponents involved is as abstract as the result that I said. It is just measurable arguments. As soon as you can define these entropies, these things are well defined. And this doesn't need. So if you have this kind of property, observe that here you do not have any fiber bundle structure. And this is the novelty of the result that is useful for other purposes. So you have a partial hyperbolic diffeomorphism. You know that in the center you are not doing very shrinking and many expansion. Then you can prove again that unstable entropy equal to the full entropy implies U invariance. So U invariance is defined like always, or almost always. It is almost everywhere defined. Everything is almost everywhere. And so far, it is in the level of invariance by some holonomy. Okay? But maybe some of you have heard, when you listen, when you hear invariance principle, some people say to me, okay, invariance principle means continuous disintegration along center foliation. But this is not. This is the invariance principle that at least I would like to name it. And it is saying that if you have zero vanishing entropy here or there in our result, previous result, what we are saying in this invariance principle, so the main comment, so the point is that if the transverse entropy of mu is 0, so what is transverse entropy? I will define transverse entropy is 0, then mu c is U invariant. So if U transverse entropy is 0, then mu c is U invariant. So what is the transverse entropy here is the difference between these two things, okay? Good. So you can imagine, of course, if the Lyapunov exponents are non-positive, again, the same technology here can be applied. So for any diffeomorphism which is quasi-isometric on the center direction, if the center Lyapunov exponents are non-positive, then you have your disintegration is U invariant. And of course, if it is 0, you can apply it for F and F inverse. You can conclude that it is S invariant and U invariant. But as majority of you should know, when you have some S invariant and some U invariant, the problem is typically going to both S and U invariant on some full measurable subset. in the proof of ergodicity, similar to the proof of ergodicity. And here, I would like to just emphasize that, so consider, I put here two invariance principles. One of them is fiber bundle case, the result with Jiagang, and quasi-isometric case. So let me suppose here something further. So suppose that the entropy of mu of f, okay, is equal to entropy S f, okay, which is equal to entropy of f. Then, and suppose that M, which is pi star of mu, has local product structure. Then what you have is that mu Cx, there exists a family of disintegration defined on the support of the measure M, which is continuous, and SU invariant. So let me see. So if I have this equality, the center disintegration is U invariant. If I have this equality, the center disintegration is S invariant. And I need to have some structure on the measure in the base. In the base here, if it has product structure, then you can prove that it is continuous and SU invariant. You can define it on the support. Here, if the measure mu has CS times U local product structure, then again you get the same result. You can define a continuous family of center disintegrations such that they are SU invariant. Okay, I'm too late now. I am seeing that. Well, I decided not to use the slides. So let me just make a caricature of these invariance principles, the proof of this invariance principle, which is a lemma that appeared in their paper, which is one of the main parts, maybe, of the beginning of the arguments, far from being the proof, of course, is that a lemma, Jensen inequality, using Jensen inequality, it's saying that, let me write it. So again, I have this, some very abstract model. I have a rectangle here, R, and I have a foliation here of plaques, Fu. So suppose that I have a finite partition. Suppose that P is a finite partition. Okay? So I have a measure in the rectangle, which I call mu Cu. And I have measures on the leaves of the foliation, which I will call mu U, which are the disintegration of this measure. So you have the notion of entropy of the measure mu Cu, okay? And you have the notion of entropy of mu U, okay? Which is exactly the conditional entropy along the unstable plaques, these plaques. So this is the transverse entropy. Okay, so, okay, as you can imagine, what I need to prove is that HU of the partition is less than equal HCU of the partition. So you see the entropy along the unstable leaves is less than the entropy of the full partition. Okay, so what is entropy? This entropy is exactly equal to minus logarithm of a conditional measure, mu U, of px intersection with fux d mu. So you disintegrate your measure along the unstable plaques, okay, and intersect with each element of partition. And this one is equal to the usual definition of the entropy, integral of logarithm of mu cu x, mu cu px. This is just a sum, mu cu x, okay? Just a finite sum here. And okay, then by the Jensen inequality, you will prove, okay, so how do you show it? This one is equal to the average of, okay, so you see that the entropy, the unstable entropy is equal to the integral of minus sum of mu u x of p. So here I have sum over all elements of the partition, okay? The logarithm of mu u x of p. And then I have the of quotient measure. So you have a quotient measure here with respect to the unstable. And this is by convexity. This is less than, so this integral is defined on the rectangle divided by this unstable plaques. And this is less than sum of the p belonging to p, to the partition. The integral of, okay, this is the function x log of x minus x log of x. So this function is convex. Is it convex? I have always this minus x log x. Okay, it's this is, okay, this is concave. So this is less than minus sum of integral of mu u x p d mu tilde times the logarithm of the same thing, the logarithm of the same thing. So these guys are exactly, some of them is exactly the entropy of the measure mu cu by the very definition. So if you take this average, the average of mu u, you are taking exactly mu cu. Mu u are disintegration of, mu u's are disintegration of mu cu. So here you have the entropy. And if you have equality by Jensen, in the Jensen inequality, you conclude that these measures should be, this function should be constant, in fact. So this means that mu u's, they are equal. These measures are equal on this sigma algebra, at least. They are all equal. Okay, so this argument is exactly saying that if your transverse entropy is 0, then you have invariance by the center holonomy, which is equivalent to invariance by U holonomy. And then you should work to do it for the dynamics, not for just a rectangle, an abstract rectangle. Okay? Good. I have good time. So let me directly go to the main applications that I had in mind to tell to you about this SU invariance, etc., is the following. So another slogan: high entropy measures are hyperbolic if maximum entropy measures are hyperbolic. Okay? So what do I mean by this? Maybe like this, nothing, but it is beautiful. If you know that all of measures of maximal entropy, ergodic measures of maximal entropy are hyperbolic, then high entropy measures are also hyperbolic. So let me directly prove something, which is consider the skew product case. So in the skew product case, f from m to m, so you have C1 plus alpha, and you suppose that center Lyapunov exponent is 0, and dimension of the center is equal to 1, okay? Suppose that, furthermore, F is accessible. Okay? Yeah. Okay. What I plan to prove is that there exists epsilon and delta such that if the entropy of a measure is larger than topological entropy of F minus delta, then, so this is ergodic measure, then the Lyapunov exponent of mu is larger than epsilon. So let me show you what is behind this phenomena of high entropy measure being hyperbolic. So this happens in the center dimension 1 and in the setting of compact center. Here is compact center. Compact center leaves. The same thing will happen in some other setting, which I will not have, unfortunately, time to go through. And what happens here is that you have, in this setting, you have some measures of maximal entropy, some finitely many measures of maximal entropy, which are, some of them have positive Lyapunov exponent on center, and some of them have negative Lyapunov exponent along the center bundle. And suppose that you have a sequence of measures which converge, their entropy converge to the entropy of the map, okay? So we can assume that the center Lyapunov exponent of all of them is non-positive, if not the similar thing, just taking inverse. So what do you have here is that the entropy of mu n by Le Drapier-Young formula is equal to the U entropy of mu n, because you don't have positive exponent. Probably in this case, you have partially hyperbolic at one center dimension. There are new results by Xiaobo-Gan and Tong and Jiagang that provide, even in C1 case, this formula in this setting when you have some good splitting and you have one-dimensional center. You have entropy equal to the unstable entropy, and you know that the measures mu n, suppose that the measure mu n converges to some measure mu. So what we know is that by semi-continuity, by upper semi-continuity of the unstable entropy, you conclude that the unstable entropy of mu n converges to mu, so the unstable entropy of mu, so you know that these measures converge to h of, the entropy converges to h of f, so the entropy of mu will be exactly, it is larger than lim sup of the entropy of mu n, so this is this is equal to entropy of f, so this means that the U entropy of mu is exactly the topological entropy of f. So in particular, it is equal to the entropy of mu, the full entropy of mu. If U entropy is equal to full entropy, this means that this measure is U invariant. So mu is U invariant. Okay? So just to finish the proof, it is, this limit measure is U invariant, so you consider any ergodic component of it will be U invariant. So suppose that mu is ergodic. Of course, this is the point. Not necessarily it is not ergodic, but ergodic component of mu are U invariant. So if the center exponent of mu n, by contradiction, if center exponent of mu n converges to 0, if by contradiction, center exponents of mu n goes to 0, this means that center exponent of mu is 0, you have one dimension. So this means that, again, applying invariance principle, mu is also S invariant. So mu is U invariant by the invariance principle. It is also S invariant by invariance principle. So this means that mu is S and U invariant, and we are in the setting where I said this setting where the quotient measure is product measure. This means that using accessibility, you conclude that mu should have 0 exponent. 0 exponent. So this is called the rigid case in the classifications of MMEs for this class of dynamics. Okay. So and this is a contradiction. Yeah. What? It should be what? Yeah, in fact, this measure is an ergodic measure of maximal entropy, and in fact, in this case, F should be rotation type on the center. Yes, exactly. Yeah, okay. So I think that I will finish, and maybe we continue with Jerome tomorrow.
So, any questions? Yes.
Okay, thanks. For the last, you mentioned that there are other settings than the compact center.
Yeah. Okay, thank you. So, theorem. Suppose that F belongs to C1 plus alpha, partially hyperbolic dynamics, and it is discretized Anosov flow. So after Martin Tich thesis, we call the setting that we are working discretized Anosov flow, which is a well-known category of partial hyperbolic diffeomorphism nowadays. So you have a partial hyperbolic which is discretized Anosov flow, and this is one-dimensional center. Suppose that F is not a suspension. No, I mean the flow, underlying flow. So every discretized Anosov flow has some underlying flow. Underlying flow is not suspension, and it is transitive. So you have a transitive Anosov flow which is not suspension. You consider the discretization. It is not just time-bound math. Any time tau of the flow. So this is the partial hyperbolic diffeomorphism. What we conclude is that either you have there are two measures of maximal entropy, mu plus and mu minus, MMEs, such that the U entropy of the measure with negative exponent is exactly the topological entropy of F, and this is larger than the S entropy. So the measure with negative exponents has asymmetry, and the stable entropy is less than this one, and the stable entropy of another measure is equal to the top entropy of F, which is strictly larger than U entropy of mu plus. Or you have a unique measure mu, MME, with 0 Lyapunov exponents. So in this case, so in this setting of discretized Anosov flows, which are irreducible, we call them irreducible discretized Anosov flows. So these are called irreducible discretized Anosov flows. What you conclude, again the same thing, which tomorrow you will see that are very fancy. You will show in this setting that, again, high entropy measure, there exists epsilon and delta, such that if the entropy of ergodic invariant measures is larger than the topological entropy minus delta, then you conclude that the center Lyapunov exponent is larger than epsilon. Okay, and yeah. This shows in particular, just to finish, this shows in particular that there exist measures which are MME, but not UMME. So you have measures which are measures of maximal entropy, but they are not U maximal entropy, as you see exactly in the announcement of the theorem. So here, mu plus is a measure which maximizes entropy, but its unstable entropy is strictly less than the entropies. So this means, okay, so this is equal to HU top of F. So HU top, in the topological level, the unstable and the stable are equal. Their entropy is equal in this setting. But what I'm saying is that there are measures that see maximally the entropy, but they lack to see the maximal unstable entropy. Okay?
Thanks. Any other questions? Yes?
Okay, I was wondering about your theorem about to obtain U invariance of this family of measures when you consider the fiber bundle map with center not positive Lyapunov exponent with circle center ellipse. Do you believe that this is hold for compact center ellipse?
What I announced for you, if all of the Lyapunov exponents are non-positive, okay, and if the part of invariance principle is okay, it is U invariant. If you know that, I announced the result, if the U entropy is equal to the quotient entropy, then it is U invariant. So it is not necessarily one-dimensional.
Okay.
The first abstract result is not one-dimensional. But the next one, when you apply to study measures of maximal entropy, you need one-dimensionality because the entropy in the higher dimension compact set may be hidden inside this compact set.
And the setting of the quasi-isometry on the center, it's also gives the same result?
Gives a what?
The same result. The same result.
The same result, which, as I said, in the quasi-isometric, you mean higher dimension?
Yeah.
The quasi-isometric condition is higher dimension again. You have the center, yes, it is higher dimension. The invariance principle part is higher dimension. As soon as you have that entropy is equal to the full entropy, then it is higher dimension, yeah.
Okay, thank you.
Okay, so we have a very short break, 5-minute break, and then the last talk of the morning.
Okay.